Lab 3 of Physics 2211, Black Hole and Orbits. The lab is divided into two components. In the first component, the purpose is to analyze the star's motion in a unique trajectory and find net force to estimate the mass of a black hole. A preview of a result is that we estimated the mass of the black hole to be 9.74 times 10 to the 33 kilograms. In the second component, the purpose is to simulate the interactions between a planet, a spaceship, and its moon to determine the initial velocity that it takes for the spaceship to achieve a stable orbit. And in this one, we're preferably looking for a figure 8. We ultimately found that the spaceship's trajectory and the moon orbit overlap but never intersect at the same time. We were also unable to achieve a stable figure-8 orbit. Some key concepts that we'll cover include Newton's second law and gravitational force. Newton's second law states that an object's acceleration is directly proportional to the net force acting on it and inversely proportional to its mass. This helps us update position with kinematic update formulas. Gravitational force describes the attraction between any two masses. Its magnitude is dependent on two key factors: the mass of each object and the distance between their centers. When analyzing motion in curved paths like orbits, we should break down the forces and acceleration into parallel and perpendicular components. The parallel component of force causes a change in the speed of an object, while the perpendicular component causes a change in the direction of an object's motion. And then we see the same equations. Newton's second law, which allows us to calculate motion. Position velocity update formula shows the velocity and position at each step by taking into account net force, and gravitational force formulas are used in part 2, where we see gravitational attractions. For part 1, we're analyzing a star's motion in a unique trajectory. We're given a starter code and we're given a unique trajectory, and we're putting initial values to find the mass of a black hole. Our initial conditions are the mass of a star, which is 2.0 times 10 to the 30 kilograms, and our change in time is 86,400 seconds. Our system is a star and black hole, and our surroundings are everything else acting on the star and the black hole. The image shows us the glow script code for part 1 of the lab. The left image frames our initial conditions stated in the last slide. The right image shows us our code inside of the while loop, creating the trajectory of the object. We see calculations for Fnet as change in momentum over time and calculations for change in momentum in the parallel direction. This allows us to calculate Fnet parallel and Fnet perpendicular. Reorganizing the gravitational formula allows us to find the mass of the black hole. Here are the results for part 1. Throughout the trajectory, Fnet perp changed much more than Fnet parallel, showing that it had much more of an influence on the trajectory, and that being direction. And we calculated Fnet as the magnitude of Fnet as 8.7 times 10 to the 28 newtons, and the mass of the black hole as 9.7 times 10 to the 33 kilograms. For part 2, we used the starter code and the unique trajectory given, and we calculated all the forces on the moon and on the spaceship using the universal gravitational equation, and we plugged in initial velocity conditions until the trajectory is close to a figure 8. So here were our given initial conditions, and we found that the system is the spaceship, moon, and planet, and the surroundings are everything else acting on it. So the screenshots above show our computational model for part 2 of the assignment. The initial conditions from the setup are shown in the left image, and the right image shows our calculations for net force. Here we see the implementation of the gravitation equation in all the Fnet forces. And for the R, for the radius, we found it's just position 1 minus position 2. So, what were my conclusions? I was unable to create a symmetrical figure 8 orbit between a moon and its planet with initial velocities. However, by trial and error, I was able to get to this image which shows two intersecting elliptical orbits with the initial velocity as negative 25,000 and 25,000. So, what are some sources of error? Well, there are definitely some external forces in part 1 that we didn't account for, because our assumption was that there are no external forces acting on the system. For part 2, achieving that figure 8 orbit was largely a process of trial and error with initial velocities, and finding the exact perfect initial velocity for a stable specific orbit like a figure 8 is computationally intensive and often requires numerical optimization methods beyond simple guessing. So for our discussion, how is the parallel and perpendicular components of net force related to that of change in momentum? Well, they are the same mathematically. It is much easier to calculate change in momentum than change in net force, because change in momentum just needs a velocity, and change in net force, we need to find all of the forces acting on the system. What if we wanted to predict the motion of an entire system? You would need to include all gravitational interactions acting on the system. The massive objects like interactions between black hole and stars dominate, while smaller interactions like planet and moon are less dominant. Thank you.